Introduction. A cosmic descent begins. The lure of the Abisang, the silent fabric of the universe. There are places where time trembles. Light is swallowed, and the laws of physics fray at the edges. These places are not merely voids. They are cosmic monarchs, shaping the motion of galaxies and commanding the rhythm of stars. They are supermassive black holes, hidden at the hearts of galaxies, including our own Milky Way. These titanic enigmas possess masses, millions, or even billions of times greater than our Sun. Yet, they offer no visible, surface-only, an invitation into darkness where gravity reigns with unmatched authority. But what truly lies beyond the shimmering edge of a black hole? What happens when one crosses the invisible boundary, the event horizon from which not even light can return? What would we see? What would we feel? Would time slow to a halt? Would space twist into knots? Or would the very concept of reality begin to unravel? This journey is not one we could survive in body, but it is a voyage we can take in thought. Guided by the rules of modern physics, from general relativity to quantum theory, we will descend into the theoretical heart of a supermassive black hole. From the accretion disk's searing edge to the unfathomable singularity at its core, we will venture inward, layer by layer. This is not a story of destruction, it is a story of cosmic exploration, of what happens when we dare to imagine the impossible and follow gravity to its most mysterious destination. Prepare to cross the threshold. The journey inward begins now. Chapter 1. Event horizon. The point of no return. The journey begins not with a crash or a scream, but with an invisible Vela border in space, utterly silent, utterly final. It is not a wall, nor a barrier in any traditional sense. It has no color, no texture, no shimmer. But it is the ultimate threshold. Cross it, and return becomes impossible, not due to force, but to the absolute dominance of gravity over space and time. For a supermassive black hole, the event horizon can stretch over millions of kilometers. Around it orbits the chaos of the accretion disk, a radiant swirl of superheated gas and dust spiraling at near light speed. From a distance, this disk glows with a fierce brilliance, an inferno created not by fire but by friction and gravitational compression. Yet even its blinding light cannot escape once it drifts past that invisible boundary. As you approach the event horizon, time begins to behave strangely. From the perspective of an outside observer, you seem to slow, to hover indefinitely just above the edge. Your fall appears frozen in time, stretched infinitely across space. But to you, nothing changes. You continue to drift forward, unaware that your passage has become a ghostly illusion to those left behind. The curvature of space becomes extreme. The very geometry of reality warps, funneling all directions inward. Light begins to bend in unnatural arcs. If you were to shine a flashlight ahead of you, the beam would curl, not because of some interference, but because space-time itself is no longer flat, has been twisted and funneled toward the heart of the singularity. The horizon itself is not a violent place. You wouldn't feel a bump, a jolt, or a rupture as you cross it. There is no alarm, no cosmic drumroll. It is a quiet surrender. Physics still behaves, at least for a moment, in ways that feel familiar. But the truth is, you've entered a region where the map of space-time folds in on itself. An escape is no longer an option. Communication ceases. No signal, no message, no cry for help can ever cross back into the universe. Information, once it slips past the event horizon, is sealed away from the rest of reality. This is what gives the black hole its name, not because it's dark, but because nothing, not even the fastest force in the universe, light, can leave. To imagine falling past this limit is to abandon the comforts of our known universe. It is to let go of time as a steady flow, of space as a predictable path. Inside the event horizon, every future leads inward. Every second carries you deeper. There is no freedom of movement. Gravity has taken full command, and yet, despite its terrifying reputation, the event horizon is also a place of sublime mystery. It marks the boundary between what we know and what we cannot know. A frontier not only in space, but in understanding. A gateway into a region where time, space, matter, and energy dance to rules we've barely begun to grasp. You have now crossed it. The journey cannot be reversed. From here on, every moment takes you closer to the unknown heart of the abyss. Ahead lies spaghettification, light warping forces, and the possibility of encountering truths the universe itself may have hidden. Welcome to the other side of the sky. Chapter 2: Spaghettification. When gravity stretches time and flesh. Once past the event horizon, the descent accelerates, not just in speed, but in strangeness. In this domain, gravity is no longer a gentle curve in the landscape of space-time. It is a ferocious gradient, a slope so steep that even the difference between your head and your feet becomes a matter of life and death. This is where the phenomenon known as spaghettification takes over. The center of a supermassive black hole. Gravity is pulling on every atom of your body, but it does so unevenly. The closer part, surf feeder, tugged more strongly than the part further away your head. It's not a gentle tug. It's a stretching, relentless, increasing pull that grows with every meter you descend in a stellar mass black hole. This process would be violently rapid. The gravitational gradient is so steep, the forces so intense, that a human would be torn apart well before even reaching the event horizon. But in a supermassive black hole, where the event horizon spans millions of kilometers, the story is different. The tidal forces near the outer regions are more spread out, more forgiving. You could cross the event horizon without noticing anything unusual at least, but as you venture deeper, those forces grow. Millimeter by millimeter, the pull begins to differ across the length of your body. At first, it's subtle, perceptible, even, but then, slowly, it becomes profound. Atoms themselves are strained, molecules pulled apart. You are elongated, stretched into a thin filament of matter, a strand, a thread, a human turned to spaghetti by gravity's immense differential. This isn't limited to the human body. Entire stars suffer this fate. Gas clouds, rogue planets, even light becomes distorted, wrapped into whirls as the pull intensifies. Gravity, in this environment, is not a background for Sit is the sculptor, reshaping reality according to its will. Time, too, begins to unravel. While outside observers would perceive your fall as frozen or slowed to infinity, inside, time flows onward. But it does not feel right. Moments seem to drift into each other. Seconds stretch. Cause and effect wobble in strange ways. Even your sense of self might feel different as neural signals try to traverse a body that no longer behaves like a unified whole. And yet, this process is purely gravitational. There is no friction, no tearing in the way we understand it. It is space itself that is changing, and you are caught in its evolution. Your body, your atoms are simply responding to a curvature that deepens without end. For theoretical objects like spacecraft or perfectly durable instruments, this process offers data. Scientists imagine probes that might one day fall into black holes, relaying information until the last possible moment. But for living beings, this is the limit of the journey in any physical sense. Still, in our imagination, we continue. What lies ahead is more than physics. It is paradox, mystery, and perhaps insight. Beyond spaghettification lies the realm of frame dragging, where space no longer stays still, and the very concept of direction begins to dissolve. Prepare yourself. Space is about to twist. Chapter 3. falling in the view from a safe distance before we descend deeper. Let us pause for a moment and look at the journey from another perspective, not from within the fall, but from the outside. Because, for all its horror and mystery, the plunge into a supermassive black hole is perhaps most astonishing when seen from afar. Imagine a spacecraft orbiting safely at a distance, circling the accretion disk like a cautious observer. From this position, equipped with the finest instruments and a view unspoiled by gravitational distortion, the sight of someone or something falling toward the event horizon is nothing short of surreal. As the object draws closer to the horizon, it begins to slow not in reality, but in appearance. To outside eyes, the fall becomes sluggish, as if time itself resists the descent. Colors stretch. The once familiar figure grows redder and dimmer, affected by gravitational redshift. Light leaving the object must climb out of an ever-deepening well of gravity. And as it does, it loses energy, its wavelengths elongating, sliding into the infrared. Then the radio. Then nothing. Eventually, the falling figure appears to freeze locked. Just above the horizon, suspended in a moment that never ends. In truth, the fall continues. But from this vantage point, it seems time has stopped for the traveler. This is not an illusion. It's a real consequence of general relativity. Time and space bend so severely near the event horizon that what is seconds for the falling object becomes years, decades, or even millennia for the outside observer. It's as though the black hole is swallowing not just mass, but history. The object becomes a ghost, an eternal echo at the edge of nothingness, silently marking the place where time breaks apart. Now consider this. While the falling traveler sees time pass, normally heartbeat after heartbeat, thought after thought, those watching from safety might witness civilizations rise and fall, stars burn out, galaxies shift across the heavens. The falling traveler may reach the singularity in moments, while from the outside, the entire universe grows old. This discrepancy is one of the most haunting aspects of black hole physics. It forces us to confront how relative time truly is, how our experience of it depends entirely on where we are and how fast we move through space. And this difference is not theoretical alone. It has been observed. The light from matter near black holes behaves exactly as predicted, growing redder and slower the closer it clings to the edge. The universe, it seems, agrees with Einstein. Space and time are not fixed. They bend and stretch. And nowhere more extremely than here, from this safe distance. The black hole remains a black hole, remains a black silhouette sphere of darkness against a star-filled canvas, but around it swirls a corona of light, a warped ring where photons circle endlessly. Some beams of light fall in, some escape. Others are trapped in limbo, orbiting the darkness until chaos or collision decides their fate. And yet, even from this distance, even in safety, the pull is undeniable. Not just gravitational, but psychological. Black holes attract more than matter. They draw curiosity, awe, fear, and wonder. From the outside, we can only watch. But from within, the story continues. Now, let us re-enter the descent and experience. What comes next? The strange phenomenon known as frame dragging, where even space and time are forced to spin. Chapter 4. Tidal Forces. The Anatomy of Gravitational Pain. The deeper you fall, the more the universe changes its tone. What began as a quiet descent past the event horizon becomes an encounter with one of the most formidable forces in existence, tidal gravity. On Earth, we know tides as the gentle rising and falling of oceans caused by the gravitational pull of the moon. But here, in the depths of a supermassive black hole, the word tidal takes on a terrifying new meaning. It no longer refers to water or rhythm, it refers to disintegration, to warping, to the violent tearing of matter by gravity's uneven hand. Tidal forces are the result of a gravitational gradient, gravity pulling more strongly on one part of an object than another. In ordinary space, these differences are negligible. But in the intense curvature near a black hole's core, the gradient becomes extreme. So extreme that every part of your body, every structure, every particle feels its own separate gravitational pull. Let's break this down. If you are falling feet first, your toes are closer to the singularity than your head. This slight difference in distance means the gravitational pull on your feet is stronger, perhaps only by a fraction at first. But the deeper you go, the greater the difference becomes. Your body is pulled into a vertical stretch, as if the fabric of your being were trying to be unraveled from end to end. Simultaneously, your sides are drawn inward. Space around you is collapsing, narrowing like a funnel toward the singularity. The result is a crushing inward squeeze along your horizontal axis. You are not just being stretched, you are being compressed, lengthened and narrowed, distorted in all directions. This is the anatomy of gravitational pain, not the kind that burns or bruises, but the kind that rewrites the physical cohesion of your form. Molecules no longer behave as they should. Chemical bonds strain. Even atomic structures begin to suffer. And yet, strangely, in a supermassive black hole, you might not feel this pain as quickly as one would expect. Because the black hole is so vast, the gradient is more gradual. You have time, maybe even minutes or hours, before the full tidal fury is unleashed. This gives room to reflect, to observe, to witness the breakdown of space-time with a consciousness intact. Imagine looking out into space as this happens. The stars behind you, already bent by gravity, begin to smear and twist. The view is no longer a stable sky becomes a spiral of light, curving inward toward the singularity. Space itself begins to flow, not metaphorically, literally, like a river rushing toward a waterfall. Space-time is moving, dragging everything with it. Even if you were to resist, to try to fly away with the most powerful propulsion imaginable, you would fail. Within the event horizon, no force in the universe can reverse your path. You are a passenger now, riding the inner current of gravity's most mysterious form. The pain is in the realization that the laws of reality are being rewritten here. General relativity predicts your path with eerie precision, yet quantum mechanics begins to murmur warnings from the depths. These two great theories, normally so reliable, start to clash in this extreme environment. What happens to matter, to energy, to information? You are no longer just falling through space. You are falling through the limits of human understanding. And yet, the journey is not over. In the depths of this descent, we now encounter frame dragging, where even the very fabric of space-time begins to spin under the black hole's immense rotation. Chapter 5: Frame Dragging, Twisting Space. Itself, as we drift deeper into the gravitational well of the supermassive black hole, we begin to sense a shift, not just in direction or velocity, but in something more fundamental. The universe around us is no longer still. It spins, and not because we are moving, but because space itself is spinning. We have entered the domain of frame dragging, first predicted by Austrian physicists Joseph Lenz and Hans Thüring in 1918, and later refined by Einstein's general theory of relativity. Frame dragging describes how a massive rotating object, like a spinning black hole, can twist the fabric of space-time around it, not just figuratively, like a spoon swirling honey in a jar. The black hole's rotation drags space and time into a spiral. The effect is almost imperceptible near most rotating objects. Earth itself creates a faint frame-dragging effect, measurable only with the most sensitive instruments, such as the Gravity Probe B satellite launched in 2004, but near a supermassive black hole. Particularly a rapidly spinning one known as occur black hole. This effect becomes profound. Imagine space as a calm lake. A non-spinning black hole would act like a stone dropped into the center, pulling inward symmetrically. But a spinning black hole creates eddies, whirlpools. The lake does not just fall, it twists, churning around the axis of rotation. This churning is not motion through space. It is motion of space. Here, within this region called the ergosphere, no object can remain still, leaving light. The ergosphere lies just outside the event horizon and is shaped like a flattened sphere, wider at the equator and narrower at the poles. Within it, space-time is dragged along by the black hole's rotation. If you try to hover motionless, to resist the spin, you would fail. There is no stationary state. Everything is compelled to orbit. It's not because you're being pushed, but because the arena in which you exist is moving. Let's visualize it. You're in a spacecraft, floating in the ergosphere, engines humming to keep you steady. But the space you occupy isn't still, it's rotating. Your very coordinates in the universe are being pulled around. Even though you feel no engine firing, no wind or thrust, your position changes as space flows beneath and around you. If you were to shine a laser outward, the beam would spiral, warped by the twisting of space-time. Photons, the fastest travelers in existence, find their paths bent and redirected. Some may be trapped, orbiting indefinitely. Others may escape, wested, flung out at odd angles. And a few, cast inward, spiral with you toward the center. Here's where it becomes truly strange. Within the ergosphere, it's possible, at least theoretically, to extract energy from the black hole. This is known as the Penrose process, named after physicist Roger Penrose. By dropping an object into the ergosphere and splitting it, one half can fall into the black hole, while the other escapes with more energy than the original. It's as though the black hole lends a piece of its rotational energy to the escaping object, a cosmic trade, a gravitational slingshot. This process isn't just theoretical. The inspiration behind ideas like black hole energy, extraction, or even propulsion, concepts in far future space travel, science fiction, maybe, but grounded in real physics. As you descend further, the twisting intensifies. The black hole's rotation not only alters the direction of your motion, it blurs your sense of time. Inside this spinning geometry, time itself is dragged along. Clocks no longer tick at consistent rates. Seconds stretch or compress depending on your direction of travel. If you move with a spin, time flows differently than if you resist it. Direction has meaning now. in a way that goes beyond north or south. Hit affects how long you live, how much of the universe you see, and your perception distorted. Stars no longer appear in their rightful places. Their light, bent by gravitational lensing and smeared by frame dragging, gathers into rings and arcs. The universe looks as if seen through a warped mirror, with multiple copies of the same stars swirling like ghosts around you. This is not an illusion. It's a natural consequence of light's journey through twisted space here direction. Itself becomes uncertain. Up, down, forward, backward. These words begin to lose coherence. Every vector curves. Space no longer obeys Euclidean logic. You are a voyager in a fluid medium, carried by invisible tides that reshape every attempt at orientation. And still, deeper you go. The ergosphere fades behind you as you approach the inner regions, where the effects of rotation blend with the overwhelming pull toward the singularity. It is here that our current physics begins to falter. General relativity predicts one thing, quantum mechanics another. The two great frameworks of modern science cannot yet agree on what truly lies ahead. But one thing is clear. In this region, reality bends to the will of the black hole. Every second forward means another leap into strangeness. You have witnessed the turning of space, the spiraling of time. You have floated through a region where the rules we trust no longer apply as they should. And now, beyond the frame-dragging winds of the ergosphere, you fall toward the seething storm of the accretion. Disks, the final orbiting fire before darkness reigns. Chapter 6. Accretion Disk, the blazing storm before the fall. Before true darkness, there is fire. Before silence, there is chaos. Before the final fall into the abyss, there is the last great storm, the accretion disk. If a black hole could have a crown, the accretion disk would be it. A luminous, spiraling halo of plasma and energy, rotating at unimaginable speeds, glowing with the heat of 1,000 suns. Though black holes themselves emit no light, the material surrounding them tells a story of violent beauty, one of matter pushed to its limits, crushed, heated, and transformed into light by the very gravity that seeks to devour it. The accretion disk is not part of the black hole. It is the last frontier before the horizon, formed by gas, dust, and shredded remnants of stars that have wandered too close. The disk flattens into a brilliant spiral, circling the black hole at relativistic speeds. Here, particles collide, compress, and radiate energy as friction heats them to millions of degrees. It is a furnace of cosmic fury. From a distance, the disk appears as a glowing ring. But as you draw closer, your view becomes increasingly distorted. Gravitational lensing bends the light from the disk so severely that you begin to see it from impossible angles, both from above and below, simultaneously. A photon orbit, sometimes called the photon sphere, surrounds the black hole like a halo of trapped light. Within this sphere, light can circle the black hole multiple times before either plunging in or escaping outward. It creates a warped and mirrored vision of the disk, a ghostly repetition of its blazing swirl. The inner edge of the accretion disk reaches a point known as the innermost stable circular orbit, or ISCO, for a non-rotating black hole. This lies at 3 times the radius of the event horizon. For a spinning black hole, it can lie much closer, depending on the direction of the spin relative to the disk. Inside this edge, orbits become unstable. Matter that ventures beyond this line quickly spirals into the black hole, never to return. But what would it feel like to pass through the accretion disk? What would you see, hear, experience? First, the heat. Temperatures here can exceed 10 million degrees Kelvin, hotter than the core of most stars. Any ordinary object metal, ceramic, even diamond would vaporize instantly. But if you could survive it, protected by hypothetical shielding beyond anything we've yet imagined, you would witness a world ablaze with energy. X-rays dominate the scene. Ultraviolet light, gamma rays, and high-frequency electromagnetic radiation bombard every square centimeter of space. These emissions are not just theoretical, they are observed. X-ray telescopes like Chandra and NUSDR have detected these furious emissions from black holes across the cosmos, painting a portrait of an inferno that screams even as it is swallowed. Second, the motion. You would be caught in a gravitational ballet, circling the black hole at speeds approaching the speed of light. Time for you would slow dramatically, dilating as Einstein predicted. An hour here could mean days, years, or centuries in the outside universe. The faster you move, the slower your clock runs relative to those who remain behind. And third, the danger. The accretion disk is not a smooth or uniform structure. It is turbulent. Vast magnetic fields twist through the plasma, creating explosive events and flares. Matter crashes into matter, accelerating particles to near-light velocities. The disk shudders with magnetorotational instabilities, unpredictable swirls that can tear through entire regions of the disk, releasing bursts of radiation that span galaxies. Yet there is a rhythm to the madness. The disk does not spiral in all at once. It feeds the black hole slowly, steadily, like rain swirling into a drain. Some black holes, particularly quasars, feed so rapidly that their disks outshine entire galaxies. Others feed slowly, glowing faintly but steadily. Ours, the black hole at the center of the Milky Way, Sagittarius A*, a quiet diner, consuming just enough to flicker faintly in the X-ray spectrum. Inside the disk, visibility is limited. Plasma and radiation scatter light in chaotic patterns. Shadows dance and flicker, distorted by gravitational lensing. Sound, in the traditional sense, cannot travel through the vacuum of space, but if it could, the disk would thunder. A roar of collisions, compressions, and high-energy interactions echoing through your thoughts like a pressure you can't escape. And amid this fury, time feels unsteady. The concept of before and after wobbles. Space does not follow straight lines. Even inertia feels different. The pull is not simply downward, inward, spiraling, dragging. You're not falling in a straight line. You're caught in a spiral dance with death, orbiting faster and faster, tighter and tighter, until the disk drops you over the edge. One final breath, one last ring of fire, and then quiet. You cross the inner boundary of the ESCO. The disk no longer supports your orbit. There is nothing but darkness ahead. The noise, the heat, the motion all falls away. You are now fully committed to the fall. No more circling, no more delay, no more orbit. Gravity takes over completely. What comes next is a realm where even light cannot escape. The electromagnetic noise of the universe falls silent. You are alone now in the deepest dark, heading toward a singularity that physics cannot fully describe. But even in this quiet, invisible place, magnetic forces still twist, and relics of the accretion disk's fury echo inward. In the next chapter, we will descend into the lingering chaos of those fields, intangible yet powerful, magnetic mayhem. Chapter 7. Magnetic mayhem, fields in the maelstrom. As the blazing fire of the accretion disk fades behind you, you enter a region where another invisible force asserts its dominion. Magnetic fields. Though unseen by the naked eye, these fields sculpt the environment around the black hole with a power rivaling gravity itself, weaving a complex web of chaos and order in the heart of the maelstrom. Magnetic fields arise naturally in space, generated by moving, charged particles, electrons, protons, and ions racing at near-light speeds. In the environment of a supermassive black hole, this process is supercharged. The intense rotation of the black hole, combined with a turbulent, electrically charged plasma swirling in the accretion disk, acts like a cosmic dynamo, amplifying magnetic fields to strengths billions of times greater than those on Earth. But why do these fields matter? Because they influence how matter moves, how energy flows, and how the black hole feeds itself in the maelstrom around the black hole. Magnetic field lines are twisted, tangled, and stretched to extremes. They thread through the plasma like invisible spiderwebs, trapping charged particles and accelerating them along spiraling paths. These charged particles then emit powerful radiation, radio waves, X-rays, even gamma rays, illuminating the black hole's environment in an eerie glow. At the same time, magnetic fields play a critical role in transferring angular momentum, the rotation from the infalling matter. This process allows matter in the accretion disk to lose energy and spiral inward. But magnetic turbulence causes the disk to heat up and fall inward, feeding the black hole in a cosmic dance of destruction and renewal. This magnetic turbulence also causes dramatic events known as magnetic reconnection. Picture a stretched rubber band suddenly snapping and rearranging its shape. Magnetic field lines can suddenly break and reconnect in new configurations, releasing enormous bursts of energy. These reconnection events can trigger flares and jets that shoot out from the poles of the black hole at near light speeds, visible across millions of light years. Indeed, some of the most spectacular phenomena in astrophysics, relativistic jets, owe their origins to this magnetic chaos. These narrow beams of plasma shoot out from the black hole's poles like cosmic lighthouses, cutting through surrounding space with incredible energy and speed. They shape the evolution of galaxies, trigger star formation, and sculpt the large-scale structure of the universe itself. But what would it be like to experience this magnetic mayhem up close? Within this region, the concept of empty space dissolves. The vacuum is alive with invisible fields, buzzing with energy. Particles spiral wildly along magnetic coils, emitting radiation that would pierce through flesh and metal alike. This radiation bathes everything nearby in a lethal glow, a relentless storm of high-energy photons. The magnetic field's influence extends even inside the event horizon, warping the environment further. Although classical physics struggles to describe conditions past the horizon, some theories suggest magnetic fields may thread through the singularity, affecting the structure of spacetime itself. And yet, despite this violent environment, the black hole's magnetic chaos is part of its complex symphony, a balance of forces that govern the most extreme regions of our cosmos. In the next chapter, We will follow these magnetic echoes as they manifest in the form of energetic radiation, the ghostly signals emitted from the void itself, echoes of X-rays. Chapter 8: Echoes of X-rays, Radiation in the Void. As we venture deeper into the shadows cast by the supermassive black hole, a surprising truth emerges. Though the black hole itself is a region where light cannot escape its surroundings, blaze with intense radiation. Among these signals, X-rays stand out, powerful, energetic echoes from the violent processes unfolding near the abyss. X-rays are a form of electromagnetic radiation, with wavelengths much shorter than visible light, carrying enormous amounts of energy. They can penetrate dense clouds of gas and dust, offering astronomers a unique window into the energetic environments near black holes. Observatories such as NASA's Chandra X-ray Observatory and ES M. Newton have captured spectacular images of these X-ray emissions, revealing dynamic and chaotic regions shaped by gravity and magnetism. But how are these X-rays created? The answer lies in the extreme conditions of the accretion disk and the turbulent plasma swirling within it. As matter spirals inward, gravitational forces accelerate particles to relativistic speeds, a significant fraction of the speed of light. These high-speed charged particles interact with magnetic fields, emitting radiation in the form of synchrotron and inverse Compton processes, both key sources of X-ray photons. Synchrotron radiation arises when electrons spiral along magnetic field lines, releasing energy in the form of light. Inverse Compton scattering occurs when high-energy electrons collide with low-energy photons, boosting the photons to X-ray energies. Together, these mechanisms illuminate the space around the black hole with a harsh, high-energy glow. The X-rays provide more than just spectacular views. They encode critical information about the environment near the event horizon. By analyzing the energy, timing, and distribution of these emissions, scientists can infer the geometry, density, temperature, and magnetic properties of the accretion disk and surrounding plasma. They reveal how matter behaves under conditions impossible to replicate on Earth. These X-ray signals also vary over time, flickering and flaring unpredictably. Such variability hints at dynamic processes, magnetic reconnection events, shocks, and turbulence within the accretion disk and corona, the hot, tenuous region of plasma hovering above it. These changes may last from seconds to hours, reflecting the complex and volatile nature of the black hole's feeding habits. In some cases, powerful X-ray flares precede the launch of relativistic jets, beams of plasma that shoot out from the black hole's poles at near-light speeds. The connection between these jets and X-ray emissions remains an active field of study, linking magnetic mayhem to large-scale cosmic phenomena. Interestingly, despite the violent origin of these X-rays, the environment near the event horizon is paradoxically silent in other ways. The vacuum of space cannot carry sound, and no traditional signals can escape from inside the horizon. The X-rays we observe come from just outside the point of no return, glowing like the final cries of matter before it disappears forever. 4. A hypothetical observer close to the black hole. These X-ray photons would form a swirling maelstrom of light, bent and twisted by gravity, illuminating the void in eerie patterns. The view would be a kaleidoscope of high-energy colors, stark against the crushing blackness beyond the horizon. As we continue inward, the radiation fades, replaced by a deepening silence and new mysteries. The quantum world begins to whisper, with phenomena like tunneling challenging classical ideas about what can or cannot cross the event horizon. Our next step leads us into the realm of paradoxes and puzzles, where the firewall hypothesis confronts the peaceful facade of the horizon. Chapter 9. Quantum Tunneling, Ghosts Through the Horizon. Chapter 9. Quantum Tunneling, Ghosts Through the Horizon in the Vast Silence Beyond the Event Horizon, where classical physics predicts a one-way journey into oblivion. The strange rules of quantum mechanics begin to take center stage. Here, the universe reveals its dual-nature particles behaving as waves, certainty dissolving into probability, and the impossible becoming just conceivable. Welcome to the realm of quantum tunneling, where particles can pass through barriers they should not be able to cross. Quantum tunneling is a phenomenon observed in laboratories and nature alike. It allows particles to tunnel through energy barriers without possessing the classical energy required to overcome them. In everyday terms, imagine a ghost passing through a locked door without opening it. This defies classical intuition, but quantum mechanics shows it to be an intrinsic feature of the subatomic world. So, how does this translate to the environment of a supermassive black hole? The event horizon, the ultimate boundary, is traditionally seen as a point of no return, no information, no matter. No light can escape once crossed. But quantum tunneling challenges this. The horizon is not a perfect wall. It's a fuzzy veil, shimmering with quantum uncertainty. Particles near the horizon can sometimes tunnel out, appearing as though they have escaped the black hole's grasp. This mechanism underpins the famous prediction of Hawking radiation, named after Stephen Hawking, who proposed that black holes are not completely black. Instead, they emit faint radiation due to quantum effects near the horizon. Virtual particle pairs spontaneously form near the boundary. One falls in, the other escapes as real radiation. This subtle leak causes black holes to slowly lose mass over unimaginable time spans. The idea of particles tunneling through the horizon reveals a profound truth. The event horizon is not an absolute barrier in the quantum world. It is a region where classical and quantum physics collide, where information may not be lost but encoded in subtle, mysterious ways. Yet this opens a Pandora's box of paradoxes. If particles can escape, what happens to the information contained in the matter that falls into the black hole? Does it vanish, violating fundamental principles of quantum mechanics? Or is it somehow preserved, encoded on the horizon's surface, or released in the radiation? Physicists have grappled with these questions for decades, leading to hypotheses such as the holographic principle and the firewall paradox concepts we will explore in the coming chapters. These ideas hint that the universe's deepest secrets lie at the intersection of gravity, quantum theory, and information. For the traveler falling inward, quantum tunneling offers no direct escape. The path still leads inexorably toward the singularity, but from the vantage point of the wider universe, it hints at subtle exchanges between black holes and the cosmos whispers from the abyss. As you descend further, the classical view of spacetime warps ever more radically. The smooth geometry predicted by relativity gives way to quantum fluctuations, making the horizon a seething quantum cauldron, alive with possibilities. The journey inward is not just a passage through space, it is a voyage into the heart of the quantum unknown. Next, we confront one of the most debated puzzles in black hole physics. Chapter 10: The Firewall Paradox, Death by Light. Chapter 10: The Firewall Paradox, Death by Light. Deep within the fabric of black hole physics, a storm brews, a paradox that challenges everything we thought we knew about the event horizon. This is the firewall paradox, a theoretical conundrum suggesting that instead of a quiet crossing, the event horizon might be a searing wall of high-energy radiation, a deadly firewall that obliterates anything attempting to pass through. For decades, physicists believed that crossing a black hole's event horizon would be uneventful, a gentle passage consistent with Einstein's general relativity. The horizon was seen as a smooth boundary, a point beyond which escape was impossible, but without violent forces to greet the traveler. However, advances in quantum information theory and efforts to reconcile general relativity with quantum mechanics have painted a more complex picture. The paradox arises from the conflict between three key principles. The equivalence principle. Einstein's assertion that an observer falling freely into a gravitational field, should experience nothing unusual at the horizon. Unitarity, the principle in quantum mechanics that information is never lost. It must be conserved, even in black hole evaporation. No cloning theorem, quantum. Information cannot be perfectly copied. Physicists trying to resolve these together found that maintaining all three simultaneously. The result, the horizon cannot be a benign boundary. To preserve unitarity and prevent information loss, the horizon might instead be transformed into a blazing firewall of high-energy particles, if true. This means any object crossing the horizon would be instantly incinerated by intense radiation. The peaceful crossing imagined by classical relativity would be replaced by a catastrophic encounter. This theory remains highly controversial. It shakes the foundations of physics and challenges long-held assumptions about spacetime and causality. Some researchers argue the firewall is unavoidable, while others seek alternative resolutions that preserve the smooth horizon and information conservation. From a philosophical perspective, the firewall paradox forces us to reconsider what it means to fall into a black hole. Is the event horizon a gentle threshold or a lethal barrier? Does the universe protect information by destroying anything that tries to cross? The debate also highlights the deep connection between gravity, quantum theory, and information, a triad at the frontier of modern physics. While the idea of a deadly firewall is frightening, it also suggests that black holes are more than cosmic vacuum cleaners. They are quantum objects, complex and subtle, whose mysteries remain tantalizingly out of reach as we journey further inward. The horizon's serene facade gives way to intense forces and paradoxes. The next chapter takes us inside the inner horizon, beyond the outer event horizon, into a region of even stranger physics. Chapter 11. No turning back inside the inner horizon. Chapter 11. No turning back inside the inner horizon. Beyond the familiar boundary of the event horizon lies a deeper, less understood frontier, the inner horizon, also called the Cauchy horizon. This mysterious region exists only in rotating, charged black holes, such as the supermassive Kerr black holes that spin at incredible speeds. Crossing this inner boundary is not just a step further into darkness, but a plunge into an arena where the very fabric of cause and effect becomes unstable and strange. Unlike the outer event horizon, which is a one-way door sealing off escape from the black hole, the inner horizon is a fragile boundary, a threshold where the deterministic nature of classical physics begins to unravel. Here, Predictions of the future based on past conditions can break down. Time itself seems to lose its familiar flow. The concept of the inner horizon emerges from the mathematical solutions of Einstein's equations describing rotating black holes. While the event horizon marks the point of no return for outside observers, the inner horizon lies deeper within, closer to the singularity, and separates two distinct regions of spacetime. But crossing this boundary comes with profound consequences. One of the most striking features near the inner horizon is the phenomenon called mass inflation. As matter and radiation fall into the black hole, they accumulate and pile up near the inner horizon, dramatically increasing the effective mass and energy density in that region. This leads to a violent instability where the space-time curvature becomes enormous, and tidal forces can spike unpredictably to imagine mass inflation. Picture two opposing streams of debris crashing into each other inside a tunnel accept. Here, the debris is energy, light, and particles, squeezed into an ever-shrinking volume by the extreme gravitational environment. The result is a powerful amplification of energy that challenges our understanding of physics. This instability raises the question, what lies beyond the inner horizon? Classical theory suggests there could be another region of spacetime, perhaps even another universe beyond it. Some solutions propose a wormhole-like structure, a bridge through the singularity to a new cosmic realm. However, the violent instabilities near the inner horizon may destroy any possibility of such smooth passage. The mass inflation singularity could act as a cosmic firewall of sorts, ripping apart anything that approaches. The inner horizon also plays a crucial role in debates about determinism and the predictability of the universe. If the laws of physics break down here, then even with perfect knowledge of the universe's past, we cannot predict what happens next. This challenges one of the foundational assumptions of science, that the future can be known if the present is known. For a traveler falling inward, the inner horizon is a place of uncertainty and danger, not just physically, but conceptually. It represents the edge of what can be known, the boundary where our mathematical descriptions begin to fail. Yet, despite its challenges, the inner horizon remains a topic of intense research and fascination. Understanding it could unlock secrets about the quantum nature of gravity, the fate of information, and the ultimate structure of space. As you move past the inner horizon, you approach the true heart of the black hole, the singularity, place where densities become infinite and space and time themselves seem to end. In the next chapter, we will confront this ultimate boundary. Chapter 12, The Singularity, where space and time end. Chapter 12. The Singularity, where space and time end. At the core of every black hole lies a point of ultimate mystery. The singularity. It is here that our familiar concepts of space and time break down completely, and where the known laws of physics reach their limits. The singularity is a place where densities become infinite, gravitational forces become unbounded, and the fabric of the universe is torn asunder. Unlike the event horizon or the inner horizon, which are boundaries in spacetime, the singularity is a location, a point, or perhaps a ring of infinite curvature. In a classical sense, it is where all matter that falls into the black hole is crushed into zero volume and infinite density. But what does this mean for our journey? Approaching the singularity is like entering a realm beyond reality as we know it. The equations of general relativity predict a breakdown Hera point where predictions become impossible, and spacetime ceases to behave in any recognizable way. Physicists often describe the singularity as a tear in the fabric of spacetime. The warping of space and time becomes so extreme that the geometry collapses into a state where distances lose meaning and the flow of time halts or reverses in non-rotating black holes. The singularity is considered a pointer, zero-dimensional object. However, in rotating black holes, like the supermassive black holes at galactic centers, the singularity is predicted to take the form of a ring singularity, one-dimensional ring spinning at the speed of light. This ring creates even stranger consequences, such as the theoretical possibility of closed time-like curves, paths through spacetime that loop back on themselves, potentially allowing for time travel. Yet, these predictions come from classical, general relativity. The true nature of the singularity likely requires a quantum theory of gravity, a theory that merges Einstein's theory with quantum mechanics, theory still beyond our reach. For a traveler falling toward this ultimate boundary, the singularity is the final destination and the ultimate enigma. What happens here? Do the laws of physics dissolve into chaos? Is information destroyed? Or is it somehow preserved or transformed in ways we cannot yet understand? One proposal to resolve these questions is that singularities are smoothed out by quantum effects, removing the infinite densities and replacing them with exotic states of matter or new geometric structures. These ideas, though speculative, suggest that singularities may not be absolute ends, but gateways to new physics. Another possibility is that singularities connect to other universes or regions of spacetime through hypothetical structures like wormholes. While fascinating, such scenarios remain purely theoretical and fraught with paradoxes. From an observational perspective, singularities remain forever hidden behind event horizons. No signal from within can escape to tell us their true nature. All we have are indirect clues, gravitational waves from merging black holes, patterns of radiation from accretion disks, and the subtle echoes of quantum processes. The singularity is the ultimate reminder of our universe's mysteries, a place where human knowledge meets its boundary, and where the journey ends not with answers, but with profound questions. As we reach this climax, we pause to reflect on the journey from distant orbit through fiery disks, twisting spacetime, quantum whispers, and paradoxes, all culminating at the heart of darkness itself. In the following chapter, we will explore the fate of information swallowed by the black hole. Chapter 13: The Information Paradox, Lost or Preserved. Chapter 13: The Information Paradox, Lost or Preserved. One of the greatest mysteries surrounding black holes is the fate of information. When matter falls into a black hole, does the information describing that matter vanish forever? Or is it somehow preserved, hidden within the black hole's depths, or released back into the universe? This puzzle is known as the black hole information paradox, a profound conflict between quantum mechanics and general relativity that has puzzled physicists for decades. According to the laws of quantum mechanics, information can never be destroyed. It is fundamental to the theory that the complete description of a system's quantum state exists eternally, even if transformed or encoded differently. On the other hand, classical interpretations of black holes suggest that any information crossing the event horizon is lost to the outside universe, swallowed irretrievably by the singularity. Stephen Hawking famously showed that black holes emit radiation, now called Hawking radiation, which gradually causes them to lose mass and eventually evaporate entirely. But this radiation appears thermal and random, carrying no discernible information about the matter that formed the black hole or fell inside. If information truly disappears, this violates a core tenet of quantum mechanics, leading to a paradox. This paradox has ignited decades of debate and research. How can the seemingly irreversible consumption of information by black holes be reconciled with quantum theory? One proposal is the holographic principle, which suggests that all the information contained within a volume of space can be represented as data encoded on the boundary of that space. In the case of black holes, this boundary is the event horizon. This means that the black hole's surface area, not its volume, encodes the quantum information of everything it contains. From this perspective, the information swallowed by the black hole is not lost, but stored on its event horizon, encoded holographically in a two-dimensional form. This radical idea revolutionizes our understanding of space, suggesting that our three-dimensional world might itself be a projection of information stored on a cosmic boundary. Other theories propose that information escapes through Hawking radiation in subtle, highly scrambled forms, a process that would require quantum gravity to fully understand. Still, some physicists propose more radical ideas, such as black hole complementarity, suggesting that information is both reflected at the horizon and passes through, depending on the observer's perspective, or that the firewall paradox disrupts information flow in complex ways. Experimentally, these questions remain unanswered. Observations of black holes focus on indirect measurements, gravitational waves from collisions, X-ray and radio emissions from accretion, DIS, but no direct evidence of information recovery has been detected for the traveler plunging toward the singularity. The information paradox may seem abstract, but it raises profound questions about the fundamental nature of reality, causality, and the ultimate fate of matter and energy in the cosmos. In the next chapter, we will explore possible resolutions to the paradox and the emerging theories of quantum gravity that may illuminate the heart of black holes. Chapter 14: Quantum Gravity, Bridging the Divide. Chapter 14: Quantum Gravity, Bridging the Divide. For decades, physicists have sought a theory that unites the seemingly incompatible realms of general relativity and quantum mechanics. Black holes, with their extreme gravitational pull and quantum mysteries, stand as the ultimate testing ground for this elusive theory. Quantum gravity. General relativity beautifully describes gravity and the curvature of space-time on cosmic scales. Quantum mechanics governs the tiny particles and forces of the subatomic world. Yet, near and inside black holes, these two frameworks clash. To fully understand what happens in the depths of a supermassive black hole, how singularities behave, how information is preserved, and what quantum tunneling truly means, we need a new, unified theory. Several approaches to quantum gravity have been developed, each offering unique insights. String theory proposes that the fundamental constituents of the universe are not point particles, but tiny, vibrating strings. These strings can exist in multiple dimensions beyond the familiar four of space and time. By including gravity naturally, string theory offers a framework where black holes might be described by strings and brains, providing a microscopic explanation for black hole entropy and information storage. Loop quantum gravity takes a different approach, attempting to quantize space-time itself. It suggests space-time is composed of discrete, finite loops woven into a granular fabric. This granularity could prevent the infinite densities of singularities by introducing a smallest possible scale, a quantum of space, near a black hole's core. Loop, quantum gravity envisions abounds, where matter might avoid total collapse, hinting at a new cosmic cycle, holographic duality, or the ADS CFT. Correspondence posits that certain gravitational theories in higher dimensional bulk spaces correspond exactly to quantum field theories on their lower dimensional boundaries. This duality underpins the holographic principle, providing tools to understand how information can be encoded on a black hole's surface. Bridging gravity and quantum mechanics. These theories are still works in progress, facing profound mathematical challenges and awaiting experimental confirmation. However, they mark crucial steps toward deciphering the quantum nature of black holes. Understanding quantum gravity is not just academic touches on the deepest questions about the universe. What is space? What is time? How does reality emerge from the quantum substrate? And what lies beyond the singularity? For our journey inward, quantum gravity promises a new horizon of understanding. It might reveal that singularities are not the end, but gateways to new physics, perhaps even new universes or dimensions, while the details remain elusive. The pursuit of quantum gravity energizes physics, transforming black holes from cosmic curiosities into laboratories of the fundamental fabric of reality. As we move forward, the mysteries grow deeper, and the boundary between known and unknown blurs. Next, we will explore the fascinating concept of black hole complementarity, a perspective that seeks to reconcile conflicting views about what happens at the horizon. Chapter 15: Black Hole Complementarity. Two Truths, One Reality. Chapter 15: Black Hole Complementarity. Two Truths, One Reality. Black holes present one of the greatest puzzles in physics. How can two seemingly contradictory realities coexist without conflict? Enter the principle of black hole complementarity, a bold idea proposed to reconcile paradoxes about what an observer experiences falling into a black hole versus what an outside observer sees. According to classical general relativity, an observer crossing the event horizon experiences nothing unusual at the boundary, a smooth, uneventful passage inward. However, an external observer never sees anything cross the horizon. Instead, matter appears to freeze and fade as it approaches the edge due to extreme time dilation and redshift. How can these two views both be true? Black hole complementarity suggests that they are both true, but from different frames of reference. For the outside observer, information about infalling matter is encoded on the event horizon, never truly crossing it. For the infalling observer, they pass through the horizon unharmed experiencing an interior region of space-time. This duality implies that there is no single, absolute reality describing the fate of information. Instead, reality depends on the observer's perspective. The horizon acts like a cosmic hologram, encoding all information on its surface for the outside universe, while for the traveler, the black hole's interior remains a continuous space-time. Crucially, this principle aims to preserve both the laws of quantum mechanics, information, conservation, and general relativity, smooth horizon crossing, without invoking paradoxes like firewalls. The implications are profound. It suggests that the universe may be more relational and observer-dependent than classical physics allows. Space and time become flexible concepts, woven from information accessible differently depending on viewpoint. Black hole complementarity also plays a key role in the ongoing debate about the nature of spacetime and quantum gravity, offering clues that a more complete theory may incorporate observer perspectives as fundamental elements. For the traveler inside, the horizon is a doorway to a mysterious interior. For the outside observer, it is a shimmering boundary storing secrets. Both realities coexist, neither more real than the other, woven together by the fabric of the cosmos. As our journey continues, we will explore further the entanglement of information and spacetime in the context of black holes, diving next into the ER equals EPR conjecture, a fascinating hypothesis linking wormholes and quantum entanglement. Chapter 16, E equals EPR, the cosmic connection. Chapter 16, equals EP, are the cosmic connection. In the quest to understand the deepest mysteries of black holes, an astonishing hypothesis has emerged, uniting two seemingly unrelated phenomena: wormholes and quantum entanglement. This idea, known as equals EPR, proposes that these are two sides of the same cosmic coin. The initials come from two landmark concepts in physics. Refers to Einstein-Rosen bridges, or wormholes, hypothetical tunnels connecting distant points in space-time. Predicted by Einstein and Rosen in 1935, EPR stands for Einstein, Podolsky, Rosen, the trio who formulated the concept of quantum entanglement, a phenomenon where particles become linked so that the state of one instantly influences the state of another. No matter the distance, at first glance, wormholes and entanglement seem unrelated. Wormholes are classical geometric objects that might connect distant regions of the universe, while entanglement is a purely quantum phenomenon, a mysterious, non-local connection defying classical intuition. But equals EP boldly suggests that entangled particles are connected by tiny, microscopic wormholes, quantum bridges that weave spacetime and quantum information into a single fabric, if true. This would revolutionize our understanding of spacetime, suggesting that the connectivity of the universe on a quantum scale is literally a network of tiny wormholes. This idea provides a potential mechanism for how information might travel between entangled particles and offers insights into the black hole information paradox in black holes. R could explain how information escapes despite the event horizons. No escape rule. Entangled pairs formed near the horizon might be connected by wormholes that allow subtle information transfer, preserving unitarity and resolving paradoxes without violating relativity. The concept also implies that spacetime itself is emergent, arising from the entanglement of quantum states. In this view, the geometry of spacetime is not fundamental, but built from the patterns of entanglement. A profound shift in how we perceive reality. Experimental evidence for E equals EPR remains elusive. But ongoing research in quantum gravity, string theory, and quantum information theory continues to explore this fascinating connection. For the traveler inside a black hole, R suggests a deeper interconnectedness beyond the horizon, cosmic web, linking the singularity, horizon, and the universe beyond in a subtle quantum dance. As we proceed, we will delve into the final mysteries and speculative ideas about what lies beyond black holes, including possibilities of escape, new universes, and the future of black hole physics. Next up, Chapter 17, Beyond the Singularity. Chapter 17, Beyond the Singularity, New Universes and Cosmic Rebirth. The singularity, the enigmatic heart of a black hole, has long been considered the ultimate end, a point where all known laws of physics collapse and space and time themselves cease to exist. Yet, some of the most daring theories in modern physics suggest that the singularity might not be a final destination, but rather a cosmic gateway, bridge to new universes, fresh beginnings, and an eternal cycle of rebirth. These ideas, though highly speculative, arise naturally from attempts to reconcile general relativity with quantum mechanics and to understand the fundamental nature of spacetime. One such concept is that the intense gravitational collapse forming a black hole does not crush matter into a singular point of infinite density, but instead triggers a bounce akin to a cosmic heartbeat. Quantum gravity effects may prevent the formation of a true singularity, replacing it with a region where spacetime is stretched and folded in complex ways, allowing matter and energy to transition into a new phase. This leads to the hypothesis of black hole cosmology. The notion that our own universe might have originated inside a black hole existing in a higher dimensional parent universe. In this framework, every black hole could be a seed for a new universe, a cosmic womb where space-time and matter re-emerge in a fresh, expanding cosmos. Imagine a chain of universes, each born inside the depths of black holes in other universes, giving rise to an infinite fractal of cosmic creation. Our singularity, rather than being a destructive endpoint, becomes a creative beginning. Another perspective involves wormholes or Einstein-Rosen bridges, which might connect the singularity of one black hole to another distant region of space-time or an entirely separate universe. While classical wormholes are unstable and collapse rapidly, quantum effects or exotic matter could stabilize these passages, offering theoretical escape routes from the black hole's interior. From the standpoint of an infalling traveler, these ideas hint at a journey not ending in oblivion but passing through a doorway to a new reality beyond the singularity. Space-time might unfold into a newborn universe with its own laws and dimensions. However, these speculations come with profound challenges. They raise questions about causality, conservation of energy, and the meaning of space and time beyond known physics. Observationally, these ideas are difficult to test, as no information from within the event horizon can reach outside observers. Despite these difficulties, the concept of cosmic rebirth through black holes captures the imagination and inspires ongoing research in quantum gravity, cosmology, and theoretical physics. As we contemplate this grand vision, our journey has taken us from distant orbits to fiery disks through quantum paradoxes and the edge of space-time itself, arriving at a frontier where science meets philosophy. The next chapter will reflect on the role of black holes in the universe's grand design and the future of black hole research. Chapter 18: Black Holes in the Cosmic Web, Architects of the Universe. Chapter 18: Black Holes in the Cosmic Web. Architects of the universe. Far beyond the dramatic depths of individual black holes lies their grand role in shaping the cosmos itself. Supermassive black holes are not merely cosmic curiosities or destructive vacuum cleaners. They are fundamental architects in the vast cosmic web that structures galaxies, clusters, and the universe's large-scale tapestry. At the centers of most galaxies, including our own Milky Way, lurk these gravitational giants. Their immense masses, millions to billions of times that of our Sun, exert profound influence on their surroundings, orchestrating the evolution of galaxies over billions of years. One of the key ways black holes shape their environment is through feedback mechanisms. As matter spirals into a supermassive black hole, it forms an accretion disk that heats up, emitting intense radiation and powerful jets of charged particles. These jets can blast away gas clouds, regulate star formation, and redistribute matter across vast distances. Such feedback is essential to explaining observed galactic phenomena, such as the correlation between a galaxy's central black hole mass and the velocity of stars orbiting its core, the so-called m-sigma relation. This connection suggests a co-evolution of black holes and their host galaxies, entwined in a cosmic dance that governs growth and structure. Black holes also influence the cosmic web, and galaxies stretching across hundreds of millions of light years. Their energetic outflows can heat surrounding gas in galaxy clusters, preventing runaway cooling and starburst events, thus stabilizing these massive structures. Furthermore, the mergers of supermassive black holes occurring when galaxies collide release colossal bursts of gravitational waves, ripples in spacetime that carry information about the universe's most violent events. Detecting and studying these waves opens new windows into black hole dynamics and cosmic history. Black holes' roles extend to the mysterious dark matter and dark energy realms as well. While the nature of these enigmatic components remains elusive, black holes might offer clues or interact with these fundamental constituents, influencing cosmic acceleration and structure formation for the cosmic traveler. Black holes are not merely points of destruction, but engines of creation and change. They govern star birth, galaxy evolution, and the grand architecture of the universe. Our journey to the center of a supermassive black hole reveals not only the extreme physics at their core, but also their profound impact on the cosmos at large. In the next chapter, we will explore the fascinating topic of Hawking radiation and black hole evaporation, the slow fading of these cosmic giants over unimaginable eons. Chapter 19, The Last Breath, Hawking radiation and black hole evaporation. Chapter 19, The Last Breath, Hawking radiation and black hole evaporation. Despite their seemingly eternal presence and immense gravitational grip, black holes are not truly immortal. Thanks to groundbreaking work by Stephen Hawking in the 1970s, we know that black holes emit a faint glow of radiation now called Hawking radiation that slowly drains their mass and energy over incredibly long timescales. This process, though imperceptible for massive black holes, suggests that black holes will eventually evaporate, leaving behind only echoes in the fabric of spacetime. Hawking's insight came from combining quantum mechanics with a curved spacetime near the event horizon. Quantum theory predicts that empty space is never truly empty. It teems with virtual particle pairs that spontaneously appear and annihilate almost instantly. The event horizon, one particle can fall into the black hole while its partner escapes, becoming real radiation emitted into space. This radiation carries away energy, causing the black hole to lose mass, a phenomenon contrary to the classical view that nothing can escape from a black hole. The rate of evaporation depends inversely on the black hole's mass. Smaller black holes radiate faster, while supermassive black holes lose mass at an incredibly slow rate. For supermassive black holes, the evaporation time far exceeds the current age of the universe by many orders of magnitude, making Hawking radiation a faint whisper in their vast lifetimes. Still, the theoretical process holds profound implications for the fate of black holes and the universe. As the black hole shrinks, its temperature rises and the radiation intensifies, leading to a final burst of energy before disappearing completely, though this end stage remains speculative, pending a complete quantum gravity theory. Hawking radiation also ties directly into the information paradox. If black holes evaporate completely, what happens to the information about the matter they consumed? This question drives much of modern research into quantum gravity, black hole thermodynamics, and the fundamental nature of reality. For an observer watching from afar, the black hole's last breath is a gradual fading, a slow release of energy that speaks to the deep connections between gravity, quantum physics, and thermodynamics. Our journey to the heart of a supermassive black hole reveals not only the extremes of physics, but also the delicate balance of forces that govern life and death on cosmic scales. Next, we will conclude with a reflective chapter on the mysteries and future directions of black hole research. Chapter 20, Into the Unknown, the Future of Black Hole Science. Chapter 20, Into the Unknown, the Future of Black Hole Science. Our journey has taken us from the glowing outskirts of the accretion disk to the mysterious singularity at the core of a supermassive black hole, exploring the paradoxes, quantum mysteries, and cosmic roles these enigmatic giants play. Yet, as profound as our current understanding is, black holes remain among the greatest frontiers of modern physics, shrouded in questions and ripe with possibilities. The future of black hole science is poised to be as exciting and transformative as its past. New technologies, telescopes, and experiments promise to deepen our insights and challenge our assumptions. One of the most promising advances is gravitational wave. Astronomy. Since the groundbreaking detection of gravitational waves in 2015, caused by colliding black holes, scientists have opened a new window into the universe. Future detectors, both on Earth and in space, will capture more subtle signals, revealing the dynamics of black holes in unprecedented detail. The Event Horizon Telescope (EHT) collaboration stunned the world with the first direct image of a black hole's shadow in 2019. Continued observations will refine our understanding of black hole environments, test general relativity under extreme conditions, and perhaps uncover surprises lurking in the shadows. Meanwhile, theoretical physicists race to develop a consistent theory of quantum gravity, bridging the divide between the infinitely large and the infinitesimally small. This quest will unlock secrets about the nature of space-time, information, and the birth of the universe itself. Questions such as the resolution of the information paradox, the true nature of singularities, and the existence of phenomena like firewalls or wormholes will drive research and debate for decades to come. Beyond pure science, black holes inspire philosophical and existential reflection. They challenge our understanding of reality, the flow of time, and the limits of human knowledge. As we stand on the brink of new discoveries, black holes remind us that the universe is a place of wonder, mystery, and endless exploration. Their darkness beckons us not just to fear, but to learn, imagine, and journey inward into the heart of the cosmos and ourselves. Thank you for joining this voyage to the center of a supermassive black hole. The adventure continues, and the universe awaits. Reflections from the edge of darkness. As our journey comes to an end, we pause to reflect on the vastness and mystery of the cosmos we have explored. Supermassive black holes are not merely objects of destruction, but gateways to understanding. The universe's deepest secrets, where gravity, quantum mechanics, and information intertwine in a cosmic dance. Though much remains unknown, the pursuit of knowledge about these enigmatic giants continues to inspire awe and wonder. Each discovery peels back another layer of mystery, revealing new questions and new frontiers. May this voyage kindle your curiosity and remind you that the universe is a boundless realm of discovery, inviting us to explore beyond the visible, to seek truth in the shadows, and to embrace the beauty of the unknown. Thank you for traveling to the very heart of darkness, where the light of understanding still shines.